I'll be going over my open source library for building logic on the fly, and it's called Bauhaus. So some background for the library and what it does is the area is in logic. So this is kind of a throwback to any logic classes we've taken in the past. And some of the background is in propositional variables, clauses, and CNF. So the logical sentences that we build with Bauhaus consists of logical symbols like and, or, and not. And a propositional variable is a Boolean variable that can be the X variable or its negation. So it can take on two different values. And a clause is a disjunction or of propositional variables. And a CNF is the conjunctive normal form. So it can be the form in which a logical sentence can be constructed. So specifically, it's the conjunction of clauses, so the and over ors. And a really important fact is that every Boolean formula can be expressed equivalently in conjunctive normal form. So putting it together in the context of Bauhaus and where it fits in for how it's used, when people create logical sentences or theories, we think about a decision problem, a question that can be answered with a yes or no for any given input. So something like that could be, is there a good time to meet? And the given input could be meeting times and availabilities. And it can be either yes, there is a good time, or no, there isn't. And we can take these decision problems and construct them into logical sentences where we can put constraints like the availabilities of everyone and figure out which meeting times are best. So we can take that logical sentence and give it to a stat solver, which stands for satisfiability. And we can check with this logical sentence and these propositional variables, is there an assignment of true and false that evaluates the whole formula to true? And a lot of problems can be encoded into problems that are solvable by a stat solver. So bringing it back to Bauhaus and the library, logical theories can consist of propositional variables that are structured into constraints, which can be many logical sentences or clauses to represent relationships. And to find models that satisfy these logical sentences using a stat solver, we represent the constraints in the theory in general in conjunctive normal form. So the motivation for Bauhaus was that a lot of the logical theory building extends naturally to object-oriented principles because we're representing real-life relationships and systems. And the second part is building these logical theories can have a lot of repetitive and long code, and we can naturally reduce them into something simple and expressive. So Bauhaus is a library for building those logical theories on the fly, and we can take advantage of those OOP principles when someone tries to build a logical theory. So I'm going to talk a bit more about the implementation of the Bauhaus library. So before, when we were talking about constructing a logical sentence, putting it into a CNF form, and then putting it into a stat solver for solving, this is kind of what I had in mind with the Bauhaus library. You want to have an object that stores propositions and constraints, and you want to be able to give someone the ability to create those propositions and constraints in an OOP manner. And then you want to take those propositions and constraints in an object and build a theory. So in the Bauhaus library, you can create encoding objects, and you can take classes and decorate them with a proposition decorator. And that means that every time I instantiate a class, each of these instantiations are propositional variables that are stored in my encoding. And every time I decorate a class or a method in class with a constraint decorator, I'm saying that with this specific constraint method, I want it to apply to all of the objects, all of the propositional variables from this specific class, and I want that to be stored in an encoding. And then separately, if you want to add more complex constraints outside of a class structure, then you can have a direct constraint.add method, so a function that adds that constraint, and it can be over multiple classes that are decorated. It could be over specific objects or variables. And once you've got all of that together, you can then build a theory. So giving more context to what that looks like is here you're creating that encoding object, and we're going over a snippet of the representation of a tic-tac-toe problem where you have rows, columns, and marks, where a mark is the cell where you can mark with an X or an O. And if I want to create propositional variables representing these marks, then all I have to do is decorate the class mark with proposition, and each time I instantiate a mark, then that is a propositional variable with the attributes I, which is the row, and J, which is the column. And in terms of creating the constraints, so if we have the example of a class called row, then each time I instantiate row, I want to do two things. First, of course, is each instantiation is a propositional variable. And the second part is that for each of these row objects I've created, I want it to be that at most one of them are true at any given time. And for them to be true, I want to say that each row object is true if based on the marks it's associated with. So that's a specific constraint implies all. So each row object implies the marks returned. Third part is if you want to create a constraint out of many different types of objects or classes, then you can add a constraint across all of them. So at least one of the row and column objects are true. So yeah, that's a quick snippet into what the Bauhaus library looks like. And some of the design decisions that came into building it were three big things. So first was keeping the interface very simple. So for someone using it, they only have to interact with the three objects, so encoding, propositions, and constraints, to be able to build really complex logical theories. The second part is you want to build constraints dynamically. So that means that we wait until someone hits compile on an encoding object to build a constraint. So if you took the opposite, where you wanted to build it iteratively, then that would mean each time someone adds a new object, you start building the constraint right away. And that can lead to lots of redundant clauses and complexity in software. So the benefit is that if we build it dynamically, it's a lot simpler, plus it's much easier for someone to debug and catch where an error comes up. And the third part is theory introspection. So these theories can grow very large, so it's important to be able to understand where a specific clause or constraint came from. So for me, I would be able to see if I created this row object, what are the constraints that are coming from it? So yeah, that's an overview of the library, some of the design decisions, and a quick brief look into how it works. And the first version is out, so you can install it with pip, and there's a lot of documentation on the website, which you can check out and get started right away with. And next steps for the library is we are thinking about extending more of the natural ways that someone creates a logical theory. So one of them is creating constraints for a subset of propositional variables based on their attribute values. So thinking back to the class structure, a class can have an object instance has certain attributes. And we might want to group these objects based on their value for something. So say if we want to think about scheduling meetings with people, then we might want to group these meetings by the time that they happen, and specifically if they happen at the same time, and then apply a constraint to each of these subsets. And the next part is adding more optimized implementations of the constraints. Currently, they're naive, so there's a bit of a explosion in the complexity, but it's good in a way because if you add optimized, then there can be more complexity just in understanding theory itself. And then we're thinking about extending the constraint support. There's a lot more ways to encode problems and also improve the testing for the library with more interesting testing libraries out there, and also just add more examples and tutorials for people to get started. Here you can see we have the encoding object that we're creating and we're importing from Bauhaus. And for the tic-tac-toe, we have rows and columns and marks. And in the essence, like we know for tic-tac-toe that at most one row or at most one column must be true for there to be a win. And yeah, those are pretty much like the simple rules for tic-tac-toe, where at most one of these must be true at any given time. And for something to be true, for a row or column to be true, it must imply that the marks in it are valid. So this code, you can see the Bauhaus decorators here for adding the constraints. And then after having defined those classes with proposition decorators and constraint decorators, we can then instantiate these objects. And so we're instantiating marks, rows, and columns, and then we can compile a theory. So right there. So if I run that, you can see here, it seems like a pretty simple thing. We only have 4 constraints going on, but the theory already seems to look pretty big and daunting. So this is a theory, and what we can do then is we can actually look into theory itself. We can introspect it. So I'll just comment this out. Click. Oh, oops. Not the one. So you can see here, going from the top. So with introspection, you can look into each constraint, what function it is coming from, and any arguments that it was given. And you can analyze. So from each row object, so this is row 1, we were able to get these constraints that either this row object occurs or the other. Oh wait, sorry, this is for the marks. Right. And then you can check out the final constraints, and you can continue to do this for each of the constraints that were created. So this is for at most one of the rows being true, and you can see it applies to each row object, and the same for column, and then the other implies all for all of the columns. And then finally, you can solve the theory. This might be a little small, it's kind of hard to see. Oh, I probably should have increased the size, but it's okay. So you can see here that by passing the theory through the solver, which is the theory.solve, you can see the truth assignments to each of the mark values and the column values and the row values. And yeah, that's a quick demo.